Hello, everyone. Thank you for joining today's Slang virtual meetup. In today's session, we will take a deep dive into Slang's automatic differentiation. Our speaker today is Shannon Woods, chair of the Slang Working Group. But first, a couple of housekeeping items. If you have any questions during the presentation, please ask using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we will post a link to the recording on the Slang website. At the end of the session, please complete the short survey to help us better design future events. With that, I'll hand it off to Shannon Woods, chair of the Slang Working Group and principal graphics technical program manager at NVIDIA. Shannon?
Hey, everybody. So to set us up for a good session on how automatic differentiation works in Slang, I want to first talk a little bit about why it is we care so much about being able to generate derivatives. So imagine you're trying to operate a complex machine with 1,000 different knobs and levers, with each knob controlling a different parameter, like the color of an object or the roughness of a surface or the scale of a procedural pattern. So your goal in using this machine is to get the machine to produce a specific desired result. But in order to do that, which knob do you turn and by how much? If you just randomly fiddle with the controls, then that's going to be slow and inefficient. You're just basically guessing what you need to do to get the right result. So you need a way to understand the machine's behavior so that you can make deliberate adjustments. Basically, you need to know how each knob influences the final outcome. And that is where derivatives come in. Because derivatives tell you about the rate of change of a function at a specific point, it can tell you exactly how much the machine's output would change if you were to twist that specific knob by a tiny amount. And the collection of all of the individual derivative values, one for each knob or lever, forms a gradient. And that gradient is your guide. It's a vector that tells you exactly which way to turn each and every single knob at the same time to get closer to your goal. So by following the guidance of the gradient, you can systematically adjust the entire set of controls, and that is guaranteed to bring the machine closer to your desired output. And in the real world, there are lots of problems that can be framed this way as a machine with lots of knobs and levers. So you could think of a bitmap, for example, as a machine that has 4 knobs for each pixel, R, G, B, and A. Or a virus with just a couple of dozen genes could be thought of as a machine with a couple hundred levers and knobs controlling its replication. Getting even more concrete, derivatives are essential for tackling some of the biggest problems in computer graphics and other high performance computing. So a few examples, inverse rendering, which is the process of inferring scene parameters from a rendered image. For instance, you might have a photo of a scene and you want to figure out the exact position and color of the light source that illuminated it. So in order to do that, we could define a loss function to measure the difference between our rendered image and our reference photo, and then taking the derivative of that loss with respect to the parameters of the light, we can use a technique called gradient descent to find the best fit. Another technique you might be familiar with, which falls into the same reconstruction domain as inverse rendering, is 3D Gaussian splatting. In Gaussian splatting, you start with a series of photos and some number of splats or blobs that represent emissive points in space. And you learn the parameters of each blob, including color, position, and the parameters that specify its density and scale by defining and optimizing to reduce the difference of what your renderer creates and what the ground truth photos show. Then there's procedural content optimization. So let's say you're generating a complex procedural texture using a shader with dozens of input parameters for colors, fractal frequencies, noise scales. Manually tweaking the parameters to achieve a specific look is tedious and time consuming. So you could instead have a target image that you're trying to imitate and a loss function to measure the pixel-wise difference. Autodiff can compute the derivatives of the loss with respect to all of your input parameters, allowing an optimizer to automatically adjust them until the generated texture matches the target. Or, as another example pictured right here, this is a procedural texture of cobblestones where the bitmap levels are being generatively optimized. Normal maps are a great case for this because standard box filtering or other linear approaches that work for color data don't properly handle non-linear directional information like normals. So using Autodiff, we can find the optimal way to pre-filter the data for each MIP level. And this is actually what we did to demonstrate basic Autodiff during our neural shading course at SIGGRAPH, which I'll give you a link to at the end of the presentation. Then beyond graphics, in physics, the ability to differentiate through a physics simulation enables new approaches to modeling complex phenomena. This animation shows an oblique vortex collision simulated using the neural flow maps method. The paper's authors here use a differentiable neural network as a data primitive to model fluid flow. And then they leverage the network's differentiability to achieve better accuracy and stability in their simulation, which gave them, I think, better energy conservation and reduced numerical dissipation. So in this instance, the differentiability of the neural network itself is fundamental to the simulation, and it allowed them to solve some longstanding problems in fluid dynamic with a novel technique. So those are just a few examples to highlight why having a tool to automatically compute derivatives like Slang's Autodiff system is so important. It takes complex intractable problems and turns them into solvable optimization challenges. Okay, cool. So with that out of the way, what is automatic differentiation, which I've been calling Autodiff for short here? So at its heart, automatic differentiation is just the chain rule from calculus systematically applied to every single elementary operation in your program. It has two strategies for doing so called forward mode and reverse mode. And I'll walk you through those two approaches to see why the direction of calculation matters. But to illustrate this, I'm going to use this set of nested functions. F of g of h of x over here. And I'm also going to use this notation that just assigns the results of each step of the calculation to a subscripted x. They're the same thing. I'm just basically trying to give you multiple ways to look at it. And if this seems like more math and symbolic notation than you signed up for, don't worry. You don't have to know any of this to use Autodiff. I just wanted to give you an idea of how the flow works and help you visualize what's going on in Autodiff. So in forward mode, we compute the derivative by propagating the rate of change from the input to the output, like a ripple effect. So for every step in our computation, we'll track both the value of the calculation and how fast it's changing with respect to its input. So we'll start by taking the derivative of our initial variable, x sub 0, with respect to itself, because x sub 0 is x. So because we're taking the derivative with respect to itself, the value is 1, and that represents our initial rate of change. And as we move forward through the computation, we'll apply the chain rule at each step. So the derivative of each new variable is the product of its derivative with respect to the previous variable and the derivative of the previous variable. So we'll simply carry this calculation forward one step at a time until we reach the final output. Now you can think of derivatives flowing now from the innermost function to the outermost, kind of like this, if you see at the bottom. And then the final results, y prime, is the product of all of the intermediate derivatives. Now, in reverse mode, we compute the derivative by propagating the influence of the final output back to the inputs. So starting with the final output y, which we've also noted as x3 here. So y and x3 are the same thing. X3 is also the result of the entire calculation. We'll get the derivative with respect to x sub 2 by taking the derivative with respect to x sub 3 and multiplying it by the derivative of x sub 3 with respect to x sub 2. And just like in forward mode, we'll repeat the process, working our way backward through the entire function until we get to our initial input, x sub 0. So this flow carries the influence from the outermost function to the innermost in that direction. But at the core, what we're calculating is exactly the same. So now that you've got an understanding of how each mode works for a single variable, let's think about multiple variables, because this is where the choice between forward and reverse mode becomes more important. It all depends on the structure of your problem, the number of inputs versus the number of outputs. So in forward mode, forward mode requires a separate pass for each input variable that you want to calculate the derivative for, which makes the cost directly proportional to the number of inputs, but it'll scale very well to a large number of outputs. So forward mode is your go-to when you're asking yourself, how does changing this one parameter affect all of my outcomes? Reverse mode, on the other hand, so it does a single forward pass to record all of the intermediate values, so it knows what those derivatives are in the middle, and then backward pass to compute all of the gradients at once. So the cost there is independent of the number of inputs, but scales both with the number of outputs and the complexity of the function. And it can also incur memory costs because it has to store the results of the computation graph in the middle. But reverse mode is the workhorse of optimization because it's perfect for asking, how do all of these parameters affect this single outcome? So in real world applications, it's much more common to have optimization problems where you have many inputs in a single output. For example, millions of pixels and only one answer to, is this a picture of a cat? But there are particular cases where forward mode is the one that you want to use. For example, calculating the normal of a signed distance field model with respect to its position, because the position is just 3 inputs. So understanding forward and reverse mode helps you pick the right strategy for your problem. But how do you actually write the code to do this? All right, well, here's some code we might want to use with backward mode. On the left, I've got a function that generates some noise. Now, this is a pretty arbitrary function, but it uses a set of inputs to create noise using various calculations that involve exponents, squares, and trig functions. So like many shader functions, it's going to operate pixel by pixel, and it's got a UV coordinate and as an input to tell it which pixel we're working on. And then down here, we've also defined a loss function that tells us how different our generated noise is from an ideal noise that we're trying to learn. So the goal with this code would be to use an optimizer to minimize the loss. We want to figure out how the value changes with every small adjustment to each one of the inputs. So in order to do that, we need the derivatives of this function, compute noise, with respect to, well, the chain of functions, calc loss and compute noise, with respect to our inputs, the frequency, amplitude, and roughness, because that's going to tell us how to adjust each input to get closer to this ideal target. Now, if we were in another shading language, we'd have to write that derivative code by hand. All right, so I haven't done calculus by hand in a while, so I just got to refresh my memory on all of the rules. All right, and then I got to look up the transcendental derivatives because we've got trig functions in there, figure out what order to apply the product rule and the chain rule and all of that. And okay, there's a for loop. how do I take the derivative of a for loop? Or worse, what if it was a switch statement that branches on a parameter that I'm trying to optimize? Or what if I don't even know the concrete type until runtime, like with dynamic dispatch on an interface? That gets confusing real fast. So this is the problem. Not only are there weird control flow things you got to figure out, but it's tedious and it's difficult and it's really prone to human error. So even if you manage to write all of that out, a single mistake will mean your optimizer gets a completely wrong gradient and your whole process will fail. And that is the problem that automatic differentiation in Slang solves. So taking a look at the code again, let's look at how simple it is to get the derivative with Slang. To ask the Slang compiler to generate derivatives for us, we're going to need to make a couple of small changes to our code. All right, so the first thing we do here is we add the differentiable annotation to our calc loss and compute noise functions. This is our signal to the compiler that we want to perform automatic differentiation on the code. And then we also need to add the no diff modifier to our UV and our target parameters. This tells the compiler that even though these parameters could be differentiated, it doesn't need to generate derivatives for them. Now, why? Well, think about it like this. The knobs that we want to tune to get our noise function just right are the frequency, amplitude, and roughness parameters. Those are what control what the noise looks like in the end. The UV parameter, on the other hand, is telling the function which pixel in the noise image it's currently generating. So that's not a parameter that's being learned, and in fact, we don't want to make any changes to it. And the target parameter being passed into calc loss is the ideal result value that we're trying to guide our function towards. So we also don't want or need to generate any gradients for that. So the no diff modifier here lets us tell the compiler that it can leave those parameters alone. So with just those two small changes, we can call the backwards diff function. Now, if this function looks a little bit funky because it's got two pairs of parentheses with parameters in them, you can just think of it as the same syntax as calling a function that returns a function as or that returns a function or a pointer to a function to your synthesized backward function. So you'll simply just call backward diff on your annotated calc loss function, and you'll get the full backward pass that the compiler generated for you. When you run this, you'll get the exact gradients for frequency, amplitude, and roughness, which are the three knobs that we want to optimize. So that's it. There is no manual derivatives to do and no tedious math, just this one call. And if we wanted to visualize what the compiler generates for you when you ask it for this backward version of the function, you can think of it as looking something like this as far as the signature goes. So I put it here in italics and on a purple background to indicate that this is not code that you write, but instead our mental model of what the compiler is generating. So you might notice that the parameters for this backward version of the function aren't the same as the parameters to calc loss itself. So I'll cover that in just a moment. Okay, so backward diff automatically generates that backward pass for us, but how do we get our hands on the gradients that it computes? Well, to answer this, we're going to look at how Slang passes data to and from the backward function. So when you call backward diff, the parameters that you give it need to be transformed a little bit. For every differentiable input to your function, like frequency, amplitude, and roughness here, you're going to wrap the original value in a special differential pair type. Now, this type holds two parts: the original value, which is called the primal, or P, and a new location to store the computed gradient, which is the differential, which we've named D. Now, Slang then calls the automatically generated backward function. The function uses the primal values that you provide to compute the gradient of the loss with respect to each input. The computed gradients are written back into the differential part of the differential pair. So after the backward diff call, you can access the gradient for each input. Now, remember that we marked the UV coordinates and the target color as no diff, so they don't have to be wrapped in a pair, since no gradient will be computed for them. Now, thinking back to how we looked at the derivatives propagating in different directions for forward and reverse mode, you can see the same directionality in the forward diff and backward diff calls as well in the direction of data flow. So in forward diff, which I have down here at the bottom, the inputs become differential pairs, but the data flow doesn't change direction. The compiler propagates the derivatives forward, and the final results and its derivative are returned in this output differential pair. So the data still flows from the inputs to the outputs. Now, with backward diff, the data flow is essentially reversed. The derivative of the return value is an additional input to the backwards function. Now, this carries that initial gradient, and because it's the derivative of our floating point loss value with respect to itself, it's 1.0. The original inputs, which we wrapped in differential pairs, have become in-out differential pairs because they're not just used to read the original value, but the computed gradient is written back into them. And then the backward function itself returns void. And then, so this lets this single backward pass compute all of the gradients and return them in one go using the in-out differential pairs. All right, so we've looked at how forward diff and backward diff automatically handle data flow with the differential pair types, but you can't just slap anything inside of a diff pair and call it good. In order to be able to generate the right code, the parameters all have to be properly differentiable. Now, thankfully, the Slang compiler knows how to deal with this because it has a differentiable type system. Now, this ensures that the compiler has all of the information that it needs to track gradients and provides a safety net for developers catching errors at compile time before they can break your optimization. So that's the secret sauce that makes all of it work. And in this section, I'm going to dive into how it's designed. So to generate correct differential code, Slang needs to ensure that the data types it's working with are differentiable. And the way it's handled by the Slang language is with the iDifferentiable interface. So any type, whether it's a built-in like float or a custom user-defined type, has to conform to this interface in order for the compiler to be able to generate differential code for it. The core requirement of the iDifferentiable interface is that every differentiable type has to have an associated differential type. So this associated type is what the compiler uses to hold and manage the derivative values. So in the differential pair, this is going to be the type of the .d member. So for instance, a float has an associated differential type of float, and a float3 has an associated differential type of float3. So for any type, you can access the associated type using the type.differential property. And in most cases, the compiler is able to automatically determine it and generate the correct associated differential type for you. So you only would need to explicitly define it for specialized or complex custom types. Now, not every type can be differentiated. The core principle here is that differentiable types have to be continuous, and that's just a property of math. So discrete value types like int, uint, and bool are not differentiable because their values change in discrete jumps. So there's no smooth slope or gradient to measure. Similarly, void is not a differentiable type because it represents the absence of a value. So what is differentiable? The built-in types that are differentiable are those that represent continuous values. So in the case of scalars, that's float, double, and half. And then also any vector or matrix that is composed of differentiable scalars. Arrays of differentiable type are also differentiable. And then tuples, where all of the composing types are differentiable, are considered differentiable themselves. Essentially, if the type can represent a smooth, continuous value, then Slang's type system can handle it. This gives you a solid foundation for building complex differentiable functions. There are some special cases, pointer and reference types in particular, and that includes resource types like a read-write structured buffer or text2D. Because those types don't hold a value directly, but instead refer to a location in memory. Now, Slang does have a notion of differentiable pointer types, but it's beyond the scope of what I'm going to cover during this section. So I'm just going to hand wave in the direction of the documentation right now for those. So whether or not you're working with Autodiff, you're probably defining your own custom types. Thankfully, making a user-defined type differentiable in Slang is straightforward. Most of the work is handled automatically. All you have to do is specify that your struct or class implements the iDifferentiable interface. Now, Slang's compiler will take care of the rest by synthesizing the necessary associated differential type for you. It'll create a new type that mirrors the original structure, with each field holding the derivative of the corresponding primal field for all differentiable fields. Now, in this particular case, since all of the fields are differentiable types, the synthesized differential type will have the exact same structure as the original. The compiler will recognize this and simply use my type as its own differentiable type. Now, note that once again, the lines that you see in italics on a purple background are not what you provide in the code. This is what the compiler automatically synthesizes. Now, you can also define aggregate types that mix both differentiable and non-differentiable fields, and the compiler will still treat the type as differentiable. For example, consider this very slightly different struct. It has an integer field member where the prior one had a float. Now, because an integer is not a continuous value, it's not differentiable. So when Slang synthesizes the associated differential type for my type now, it will only include the differentiable fields. So the resulting myType.differential type synthesized by the compiler here will then look like this. The compiler will be able to track and propagate gradients through the differentiable fields and safely ignore the non-differentiable parts of your data structure. However, if you didn't want to use the type that the compiler will synthesize, you can still provide the differential definition yourself. For example, if you wanted the differential to retain the integer field, you could simply use the type alias to define the differential type as itself. And that would override the compiler's synthesis. Now, generic types can also implement the iDifferentiable interface, which allows you to write reusable code that works with any differentiable type. Now, the rules for how the compiler synthesizes the differential type are consistent with what we've seen so far. For a generic type to be differentiable, its generic parameter must be constrained to be iDifferentiable. Now, consider this struct that holds a generic type T. Since T is constrained to be differentiable, the synthesized differential type for my type will contain T's differential type. The compiler knows how to carry through this differentiability, so my type.differential will contain T.differential. Now, if a generic type is not constrained to be differentiable, the compiler will not include it in the synthesized differential type. So here, U is not required to be differential. It's not constrained. So its value cannot be differentiated. When the compiler synthesizes the differential type, then it'll only include the differentiable fields. So the resulting myType.differential will only contain T's differential, and U will be ignored. So this ensures that the system remains sound and tracks gradients for the types that can actually have them. Passing user-defined differentiable types to functions looks pretty much the same as passing built-ins. So you'll still wrap the primal and the differential in a diff pair, the same as you would for a built-in type. And you can still use the diff pair with a single parameter to zero initialize the differential. This is provided as part of the differentiable interface. You just have to have a constructor which can take that 0. So the Slang compiler can automatically handle almost anything you can throw at it. User-defined types, generics, nasty math, complex control flow. But what do you do if a function just doesn't have a derivative? Or what if you know a better, more efficient way to compute a derivative in your specific use case than what the compiler comes up with? That is where you get to take control. So Slang allows you to provide your own custom derivative functions, which gives you a flexible way to override the default behavior and optimize for specific situations, which is a pretty powerful tool, and it gives you a lot of control over Slang's behavior without making you do all of the tedious work yourself. So let me talk a little bit first about how you might know that you might need a custom derivative. In order to get a feel for that, it's useful to know what Slang does when you mark a function as differentiable. So the Slang compiler generates differential code as an IR pass after linking. And it essentially rewrites your program to add those necessary backward or forward mode differential code chunks prior to target code generation. But the compiler can only do this when there are a clear set of rules for every operation. And there's a handful of situations where that's not the case. So the first main category is opaque functions, which you can just think of this as places that the Slang compiler can't see into. Like a common example here is hardware accelerated texture sampling. Slang doesn't know what the operations inside the function are, so it can't generate a derivative. And you would need to provide a custom derivative to do what you want it to do instead. Buffer accesses are another category of this. So operations that read from or write to buffers, like a read-write structured buffer on a GPU, introduce side effects and are fundamentally hard to differentiate. So custom derivatives allow you to handle these cases safely, for example, by using atomic operations to prevent race conditions writing to a buffer. Then the third big category is functions that are numerically unstable. So some mathematical expressions can lead to issues like division by 0 or gradient explosion or disappearance. And a custom derivative can let you add safeguards to these functions to ensure that they always produce a stable gradient. Common examples here are asymptotic functions like tan, log, square root, because their derivatives close to the asymptote explode or vanish. So you know why you might need one. So how do you define a custom derivative? Well, let's take a look here at a really simple function. In this case, we're just going to sum the square of two numbers. Now, normally the compiler would figure out the derivative for you. In this case, it's very easy. But we're going to pretend that we have our own super optimized way to do this so that we can look at how defining a custom derivative works. So we can now write our own functions for the forward and backward mode differentiation. So all you need to do is simply tell the compiler to use your functions instead of its own, which you would do by marking these functions with the forward derivative of and backward derivative of annotations. And then you provide the original function that they're the derivative of to let the compiler know that they're connected. So here you can see the definitions for the forward and backward derivative that we've provided. Now notice that the forward derivative returns a pair consisting of the primal result, which is just what you get by calling square normally and directly with the primal of each input, and the derivative value, which we've calculated by hand here. In the backward derivative, we explicitly set each in-out diff pair with the primal and gradient values. Now, in reality, this is basically what the compiler would generate for you anyway, but with a simple example like this, you can see how the mechanics of defining your own derivatives work. So thinking back to the list of cases where we might need custom derivatives, let's look at how we handle one of those. In this case, we're going to do propagating gradients into a buffer. So we've rewritten our simple square function here so that instead of receiving y directly as a parameter, it's given an index so that the function has to look it up from a global buffer. Now, the index itself isn't something that you can differentiate because it's just an integer, and we know that integers are non-continuous and therefore not differentiable. So if you were to ask the compiler to generate the diff for this function, it would leave y index here unchanged. So how do you get the gradient back into that original array? The first step here is to wrap that array access in its own tiny helper function. So this function's only job is to get the value out of the array. And then you can write a custom derivative just for that tiny helper function. So in this case, what we're doing is we've created an additional global buffer to accumulate the gradients. And we know that the way that we're accessing this buffer, we can just write the gradient directly to the appropriate place in that buffer. There's not going to be a race condition, and we don't have to make it atomic. And then thankfully, we can let the compiler handle the rest of the derivation for this because we can intermingle custom and automatic derivative code. So we're not stuck writing custom derivatives for the entire complex call stack just because we had a single buffer access in the middle of it. Now, another helpful use for custom derivatives is one that I didn't mention on the handy list of places that you might need them, and it's debugging. Now, because the compiler is synthesizing the derivative code for you, it can be tricky to reason about what's going on in the guts if things start going wrong. For example, if we look once again at our square function, imagine we wanted to look at what's happening with the gradient for our y square during debugging. Now, we don't have access directly to the compiler-generated derivative to throw a printf in there, but we can throw a printf in there with a custom derivative. If we create a function called debuggrad that just passes a value through unchanged, it's doing absolutely nothing but returning the parameter that you give it, we can then also write a custom backward derivative for this function that prints out the gradient that it receives. So you can then wrap any part of your code with debuggrad to get a snapshot of the gradient at a specific point. Now, that gives you a little window into your gradient pipeline, which you can think, it can save you a ton of time when things go wrong, and you can think of it kind of like a callback for the propagated gradients. Now, once again, this lets you insert this custom functionality without committing to writing the entirety of what could be a really complex differential by hand, because Slang's Autodiff system provides you the flexibility and customizability to do this powerful stuff while still letting you make use of the automatic system for everything else. So we covered a lot of ground today, from the fundamentals of differentiation to the practical power of an automatic differentiation system. You've seen how automatic differentiation frees you from all of the tedious and error-prone process of writing derivatives by hand, and allows you to focus on building your applications for whatever you need to do. We took a look specifically at how things work under the hood with forward and backward mode differentiation and how it propagates the gradients through your code, and saw how the differential type system can help you write clean, understandable code, and while providing the tools that you need for advanced use cases like custom derivatives. So that's a lot, but there is even more than I can get into in one single presentation. So for everything else, the Slang documentation is your next best friend. It covers everything we talked about today in more detail, as well as covering the things that I alluded to but didn't have time to cover, like differentiable pointer types. And for a really in-depth look at neural shading, which is essentially the application of machine learning techniques to graphics, we've made a recording of our SIGGRAPH 2025 neural shading course available on YouTube. So I've linked it here on the resources page, and the link should be available for you in the chat. So please dive in, start experimenting, and see how Autodiff can change the way that you code. And if you hit any snags, we are always around and happy to talk on Discord, which if you use that QR code right there, it'll take you to the join for our Discord. And we're always around and really happy to answer questions. But if you have any questions right now, ask away.
Okay, the first question I have is with the noise example, the forward mode only computes the derivative with respect to one of the inputs at a time. That is, the derivative part in the differential pairs has to be 0 for all inputs apart from 1. What happens if you set it to 1 in multiple pairs? Is the result nonsense, or can it still be something meaningful?
So Kai, can you take that one? Because I don't actually know. I've only ever been a very well-behaved coder and only set the derivative of one of them to 1 at a time.
So I think this question is related to the computational efficiency regarding to the forward derivative and the backward derivative. So if let's say if you have 3 inputs, right, but you want to calculate the derivative for all the 3 inputs. If you use the forward derivative, you cannot get the derivative for each of them. You can only get the derivative for the sum of all of them. So the only way, if you want to use the forward derivative to get the derivative for all the inputs, you have to assign 0 to the others, but only keep 1. So you have to trigger forward derivative 3 times to get the derivative for each input. So that is why in a forward mode, you always assign 1 to one input, but assign 0 to the other input.
But do you know what happens if you try to assign 1 to more than one input? Like, does the compiler stop you, or do you just get nonsense results? Or
no, the compiler won't stop you, but the result will not be the derivative for one input. Let's say if I take a very simple example, let's say I have a function which compute x squared plus y squared, right? And if you assign the derivative, if you assign the dx and dy to 1, what the forward derivative will compute? It compute 2x times dx plus 2y times dy. So because dx and dy are both 1, right? So that is the result of the forward derivative. So that's why I'm saying you cannot get the result of derivative of x and derivative of y, right? So if you want to get the derivative of x, which is 2x, right, you have to assign dy to 0. So 2x times dx plus 2y times dy will equal to 2x times dx, which is what you want. So yeah, so that is what the forward mode compute.
okay, does that answer the question? Basically, like you can compute it, but it's not a sensible derivative, so it's not useful.
Great. And Kai answered some questions earlier, but like to get it on the recording. The question was for non-differentiable types like integer, unassigned integer, or bool, do we need to denote the argument by no diff?
So non-differentiable types are just considered non-differentiable. You don't have to annotate them as no diff. They're automatically, just inherently no diff, and the compiler won't attempt to generate a derivative for them.
Great. And are there tips for choosing what arguments to denote as no diff?
So no diff, basically, like if you think of it like that machine with knobs, any knob that you're trying to figure out, what do I need to set this to, the parameters that you are learning should be differentiable. Anything that is not something you're learning, so like in the case of a texture, the UV coordinates aren't something that you're learning. They're just kind of inherent to how a texture works. If there's any value that is constant or not part of the thing that you're trying to optimize, those are the things that you want to set to be no diff. So in the noise function example, the UV coordinates and the target that we're comparing in order to get our loss value are both no diff, because we're not trying to learn those. Those are the things that we know what they are going into our calculation. It's the frequency and the amplitude and the roughness that we were trying to learn. So the stuff you're learning is differentiable. The stuff that you're not learning would be non-differentiable, or you mark it as non-differentiable so that the compiler's not trying to generate derivatives for it.
That kind of leads into this other question. Since we can mark a function with differentiable attribute, does this attribute need to be explicitly added to every single function in the call stack for the overall computational to be differentiable, or is it only required on the top level entry function?
So it does. You do need to mark all of the functions in the call stack as differentiable. Basically, Slang will not generate differentiable, or not generate a forward or backward version of anything that is not annotated as differentiable. Now there's bunches of built-in functions that are kind of already defined as differentiable, so you wouldn't necessarily need to like define your own version and mark that as differentiable. But for any user-defined functions, you will need to mark them as differentiable. Otherwise, the compiler will consider them non-differentiable. You can call non-differentiable functions in the midst of a differentiable call stack. They do need to be marked as no diff. Definitely, there's some information on that in the documentation. I would say if you take a look at that and it doesn't make sense, come to Discord and we can help you dissect it.
Great. One more question had come through. I kind of lost it here. There it is. You mentioned asymptotic functions like tan and gradient and explosion. Does Slang provide handling for any common discontinuous functions?
Yeah, so most automatic automatic differentiation systems have some handling for common discontinuous functions. Slang similarly handles, just trying to think off the top of my head, like absolute value, for example, is discontinuous at 0. But Slang provides a subgradient, or just sort of like we're going to pretend the gradient here is 0. So you can differentiate functions that involve absolute value. Clamp, min-max, floor, ceiling, stuff like that. Slang does have handling for those. The asymptotic functions, because they're just kind of mathematically defined that way, there's not a subgradient automatically provided for those.
Excellent. And the anonymous attendee would like to clarify that the answer that we provided earlier means that setting multiple ones is not typically going to be something meaningful. Is that correct?
Yeah, you don't want to provide multiple ones to your forward diff pass. It just doesn't make sense. You're going to end up with a funky derivative with respect to multiple things, and it is not actually going to let you compute anything useful.
Yeah, I also want to add up to this question. So basically, if you want to get the result derivative for each input, a usually is useless. But derivative is not only used in the machine learning, right? It could be used in a lot of stuff. Like, for example, if you want to do some simulation, dynamic float, right? So you frequently need to compute the differential equation, right? So in that situation, you might need to compute the full derivative of some function. So in that case, yeah, the forward mode is actually very useful, right? Because for example, if you have a function f parenthesis x y z, right? So in some dynamic fluid simulation, you might need to compute df times dx plus df times dy plus df times dz. So that is exactly what forward mode computes. So in that case, it's actually useful. So it really depends on the scenario you want to use this.
Thank you for clarifying. Okay.
Yes, and thank you, Kai and Shannon. Thank you for teaching us about Autodiff today. We appreciate your time and effort in putting this together.